So this video and the accompanying organizer, page 307, is pretty much a catch-all for a lot of little ideas that you need to be aware of about electron configuration. But there's so little that, spending a lot of time in one class period doesn't make sense. So they're all kind of lobbed together here. So you obviously have a lot of the definitions already written down here. So you're welcome to highlight or underline or whatever you want to do for things. I think the biggest thing that I want to do is just share examples with you. That's the best way to make sure that you understand these ideas. So first and foremost, we want to take a look at something called valence electrons. And as you see the definition, valence electrons are the electrons in the highest principal energy level. All right, principal energy level, 1, 2, 3, 4, 5. So we're talking rows on the periodic table. Okay, these valence electrons are really important because those are the electrons that are going to be responsible for the chemical properties and the physical properties of the atoms, which means they're responsible for bonding. Okay, so valence electrons, if you think about it, we're talking highest principal energy level here. Okay, so 1s1, 1s2 for hydrogen, helium. So here the first principal energy level is 1. So the valence shell is 1. The valence electrons are the 1s electrons. Hydrogen has 1 valence electron, helium has 2. Okay, if we go to the next row, now we're looking at the second principal energy level. All of these elements have valence electrons in the second shell. Lithium has 1, beryllium has 2, boron has 3, carbon has 4, all the way up through neon, who has 8. Okay, then the second principal energy level is full. Okay, then we move on to the third row, so we're looking at the third principal energy level, which means now the valence is 3. And again, 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. The idea here is that the maximum number of valence electrons you're going to have in any element is dictated by how many electrons are in the s and the p combined, which means you can have a maximum of 8 electrons in the valence shell. And now you're probably asking, well, what about the D's and the F's? Well, here's why you can't have more than 8 valence electrons. Here's why D's and F's don't count. If I go to row 4, I finished 3p. I don't go to 3d next. I go to 4s. So for potassium and calcium, the valence shell is now the 4th principal energy level. And then once I get to these electrons in the 3d block, think about the definition of a valence shell. The highest principal energy level. 3 is not the highest anymore. 4 is still the highest. So any element in the D block has a valence shell that corresponds to the row that it's actually in, not to what the D sublevel is. So these 3D elements have the valence shell of 4. These 5D elements have the valence shell of 5. So the row for every element really does tell you the valence shell. And also holds true for the F block, right? 4F is in row 6. 6 is the highest principal energy level. So the row that the element is in tells you what the valence shell is. The number of electrons in that valence shell is simply the number of s and maybe p electrons that are in that highest shell. All of these elements in the D block, all of these elements in the F block have 2 valence electrons. The 2 valence electrons that are in the highest principal energy level, that the row that the element's in, essentially. Only when you get over to the P block do you get back up to the highest number principal energy level, and therefore P electrons can be in the valence shell. So one of the big ideas here is that, again, the maximum number of valence electrons for any element is going to be 8. These guys, except for helium, because the first principal energy level is only allowed 2, not 8. Every element other than helium, wow, this is an old periodic table, I just realized. Every element other than helium has 8 valence electrons if they're in this last row. These guys are called noble gases. That's one thing that's not on your list. I forgot to put that in there. So noble gases are the electrons in the last row, or not last row, last column of the periodic table. They're called noble gases because everybody is trying to be like them. They're the nobility. People, people look up to the nobility in real life. All the other elements look up to these noble gases because they all strive, elements are going to strive to be like have the valence electron configuration of a noble gas. That's what elements are going to try to do. So when elements react, they're reacting to try and get a full valence shell, and they're reacting to try and resemble a noble gas configuration. So noble gases are called inert also because they don't react. There's no need for noble gases to react because they already have a full valence shell. They have 8 electrons. They don't need to react with anything because they're already stable. A full valence shell is a really super stable configuration. So let's go back and review a little bit with those ideas. Valence electrons are the electrons in the highest principal energy level, which is either the S and the P, or just the S. Core electrons are all the other electrons. All those inner principal energy levels are core electrons. So as you go down the periodic table, the number of core electrons increases. So for example, barium in row 6 has 5 rings of core electrons, 5 principal energy levels of core electrons, and 2 valence electrons in the 6th principal energy level. What else do we have here? Valence electron, or valence shell, highest principal energy level that contains electrons. And then valence configuration. Okay, that is the electron configuration of just valence, the valence shell. So I've got some examples of elements that I want to use to kind of drive those ideas home. So I've got sodium, phosphorus, tungsten, uranium, and then down to argon, which is our noble gas. All right, so if we look at sodium, the principal energy level that is the highest is 3. So the valence shell for sodium, oops, can't spell. The valence shell for sodium is 3. How many valence electrons does sodium have? Well, it just has 1 in that 3rd shell, so the number of valence electrons is 1. Now, how am I going to write the configuration? I'm just going to use the valence configuration that you see there. So the valence configuration for sodium is 3s1, or even more useful is to simply write s1. So the valence configuration is s1. All right, if we take a look at phosphorus, same row, so 3rd principal energy level, so nothing's different. Valence shell is still 3. Number of valence electrons is now 3s plus 3p, so there's a total of 5 valence electrons. And valence configuration is going to count all of this. So for phosphorus, you would write s2p3 for the valence configuration, or 3s2 3p3, but I prefer that you guys get used to doing it this way. All right, if we go to tungsten, further on down the periodic table, okay, valence shell. As we go through our list, what's the highest number that you see? 6. Okay, so for tungsten, valence shell is 6. How many electrons do you see? Well, all I see is 6s2, so valence electrons, there's 2. And then valence configuration is just going to be s2. So now think about it. The valence configuration for any element in the D block, for any element in the F block, is going to be s2, because the highest principal energy level is just a higher s with 2 electrons. If we go to uranium, again, we're going to find the highest principal energy level. Highest number is 7. So the valence shell is 7. Valence electrons, again, are 2. Valence configuration is just going to be S2. And then if I do argon, valence shell is 3. Valence electrons is 8. There's that all, whoops, you can't see that. 8. There's that all critical number 8. Maximum number of valence electrons is 8. And then valence configuration is S2P6. That is a really good, stable electron configuration. All right, so we've talked a lot about valence. Core electrons hopefully make sense. The other thing that I want to do, now that you know what the noble gases are, I'm going to show you the shortcut way of doing electron configuration. It uses shortcut, abbreviated, there's a bunch of different words that they use. Abbreviated configuration, whatever. It bases the idea off the noble gas. Okay, so let's go back to sodium. What we're going to do is, when you do the shortcut abbreviation, you're going to find the noble gas in the row above the element. And you're going to write that in brackets. Oops, I-T-E. So for sodium, let's look. Sodium's in the third row. So the element in the row above sodium is neon. So for the shortcut version, I'm going to write neon in brackets. Okay? Then what am I going to do? I am going to write the remainder of the configuration for the row that the element is actually in. So I'm going to write the rest of the sublevels as I normally would. Okay, so sodium is 3s1. So it's going to be neon 3s1. So if you compare, have I really saved myself any work? A little bit. So this takes care of the noble gas configuration, and then I write what's left. Okay, so if I move on to phosphorus, it's going to look very similar. Phosphorus is also in row 3, just a little further down, so I'm still going to use neon. So I've got neon in brackets, and then what's left, so here's the neon, and then I've got 3s2, 3p3. Okay? When you get further on down the periodic table, this is where the noble gas configuration, or the abbreviated shortcut configuration, really helps. Okay, so let's find tungsten. Here's tungsten. It is in row 6. So I'm going to find the noble gas in the row above it. So xenon. Xenon is going to take care of, look at all this. Xenon is going to take care of all of that. By writing xenon in brackets, I've done 1s2 through 5p6. That saves a lot of time. And then I write what's left. 6s2, 4f14, 5d4. Uranium, same thing. Okay, uranium is in the 7th row in the 5f area. So I'm going to go to Rn above. Put that in brackets. Rn takes care of everything up through and including 6p6. So what's left? 7s2, 5d3. Nice, huh? Now you're probably asking, well, what about the noble gas? Can I just write argon in brackets? Nope, because if you think about the instructions, the noble gas in the row above the element, oops, you can't see that. The noble gas in the row above the element. Argon is not in the row above the element. Neon is in the row above the element. So argon would be neon 3s2, 3p6. Okay, so there is valence and shortcut version. We will get into the rest of these ideas in the second half of the video.